first of all, let me thank the organizer for maintaining this nice conference. I mean, I think it's very important for the PhD student and the postdocs, right? So it feels a little bit strange to talk about the future of high energy physics when I don't even know what we will be doing next week, right? Nonetheless, I will try, right? Let's see. Okay. Maybe I should go full screen. It will be easier. Right? Full screen. Yeah, here it is. Okay. So as the last speaker of this nice conference, I don't have to list the big question in the field that keep all of us awake at night, right? I hope that you all know of them by now. Instead, I mean, Tao asked me to talk about the tools that we should use build to answer this nice question, right? And of course, we have many of them waiting for us. I mean, according to snow mass classification, right, there is some in cosmology frontier, some in astroparticle frontier, in an intensity frontier, and also the one that maybe matters the most for us is the energy frontier, right? Nonetheless, I should say that you will probably all agree with me that these days, the best tool actually that will ensure big progress in science is nothing else than a vaccine, right? Okay, so the biggest discovery of the LHC, and maybe also the largest surprise, is that the standard model was confirmed, right? And the standard model is really the triumph of the 20th century physics, namely quantum mechanics and special relativity. And as Stefano reminded us earlier today, I mean, what did we learn from that is really that the particle is nothing else than the representation of the Poincaré group. And according to Coleman-Mandula theorem, it will be characterized by two numbers, the spin, the mass, as well as some other numbers, quantum numbers, that will describe the internal symmetry of the standard model. And we know that at least it has to contain SU3 cross SU2 cross U1, right? And this seems in pretty good agreement. I mean, we can measure the mass and the spin of all the particle, and this kind of agree with this picture. Nonetheless, there is one subtlety, namely that what is supposed to be a direct product between the spin, mass, and these internal quantum numbers actually impose some consistency conditions that are not trivial, right? In particular, if you want to have a chiral gauge symmetry, namely if you want the chirality to be invariant under boost transformation, then you need all the particles to be massless, right? And this is obviously not what we observe in nature, right? We actually know the solution to this puzzle, and the answer is simply that the short distance interaction are different than the long distance interaction as a result of the vacuum, which is not empty, but actually contains this Higgs substance that breaks the symmetry, at least non-linearly realizes symmetry. And we take it for granted, you know, that the system or the universe can break those symmetry, but this is really something which is non-trivial. This is due to the fact that you have an infinite number of degrees of freedom. For instance, it will never happen in quantum mechanics, right? So within the standard model, I mean, clearly SU2 cross U1 is broken to U1 electromagnetism that is vector-like. And this is a result of the dynamics of an elementary scalar field, namely the Higgs boson, right? So the Higgs boson is very special. I mean, the discovery in 2012 has been an important milestone for high energy physics, and many of us are still excited about it, and others, especially in other fields of science, should also be excited by it. First of all, because Higgs is really associated to new forces of different natures than the other gauge interaction that were known so far, right? First of all, there is no underlying local symmetry as far as we know. Also, the coupling of the Higgs are not quantized charge. You know, they can take a priori continuous value. And as I say also, I mean, those forces are deeply connected to the space-time vacuum structure. And I will argue that the knowledge of the value of the Higgs coupling is really essential for our understanding of the deep structure of matter, right? So if you think about the up and down quark Yukawa, you know, they're really deciding whether the proton is actually lighter than the neutron, namely ensuring the stability of the nuclei. Right? The electron Yukawa on its own also controls the size of the atoms, right? And the top quark Yukawa decides in part about the stability of the electric vacuum. And another interesting coupling that we have no real clue about is the Higgs self-coupling, you know, that controls the thermodynamics of the electric phase transition that is supposed to take place something like 10⁻⁻10 seconds after the Big Bang. and it might be responsible for the dominance of matter, of antimatter in the universe, right? So clearly, there is a need to measure all those couplings with the deepest accuracy as possible, right? And for that, we need to rely on new machines, right? And we have different choices, right? We can have a machine that collide hadrons or machine that collide leptons. They can have a circular or linear geometry, right? And all of this option comes with some pros and cons. That's what makes all this discussion very lively and very interesting, of course, right? So I won't go into all the details of all these characteristics of the various colliders, and probably I'm missing some of them, so you're welcome to add anything to me later on if you want, right? So, I mean, we certainly agree that the exploration machines are at the heart of high energy physics. Nonetheless, there is a current consensus, I think, towards the European strategy update that the best way to actually reach this energy frontier is to start with right? You're muted. No, I'm not muted. You can still hear me, no?
Yes, we can.
Okay, good. So the big remaining question is whether we'll have a linear or circular machine. And we can really summarize, I mean, the main characteristic of these two options in the following way, right? A linear collider can be extended in energy. You simply need to dig the tunnel a little bit bigger and add RF cavities. Also, with a linear collider, it's relatively easy actually to polarize a beam, in particular the electron. The positron is a little bit more complicated, but electron is quite easy. On the other hand, I mean, for the circular machine, you can easily reach higher luminosity simply because you don't lose the beam, it can circulate, right, several times. And also, because of a synchrotron radiation property, it's actually easier to accumulate a lot of luminosity at lower energy. This means that it will be easier at a circular collider compared to a linear collider, to redo some Z-pole measurement, for instance. And we will see the importance of the Z-pole measurement even in extracting the value of the Higgs couplings. Right? So in order to help maybe taking a decision about linear or circular, I would like to address these three different questions. What will be the impact of Z-pole measurement in the extraction of the Higgs coupling? What is the benefit of the beam polarization? And also, I would like to understand whether low energy is a limitation, for instance, to learn about various types of coupling, like the Higgs self-coupling or the Yukawa interaction of the top, that in priori requires to reach some high energy threshold. So concretely, we will be dealing about various projects, that were discussed at this European strategy meeting last year in Granada, and it's unlikely that actually the picture, the landscape will change very much for snow mass this year, right? So we have to deal with the International Linear Collider, which is a project in Japan, that will start at 250 GeV with a linear collider, E plus E minus. And then there are some circular options, in particular the one in China, in a tunnel of 80 or 100 kilometers, that will also collide E plus E minus, right? Starting maybe at 250 GeV and then going down to the Z-pole mass, right? And eventually this CPC will be later on moved to a hadron collider, which is called the SPPC, right? And then there are various projects at CERN, also circular colliders, starting with E plus E minus, or also maybe later on extended into hadron machine that could reach the energy frontier of 100 of TeV. You have also the option actually of colliding an electron on an hadron in order to improve the knowledge of the PDF and also to do some interesting measurement on its own. And then CERN has also its own linear option, which is called CLIC, that will be a little bit higher in energy than the linear collider in Japan. You will start at 380 GeV. So the nice thing is that actually you don't have to wait the end of the LHC to actually start working on these machines, right? And the other thing that you should notice is, of course, the timeline of all this process. And clearly, if you want to do this kind of physics, you have to stay healthy and live long, right? So clearly, there are some experimental challenges, but there are also some theoretical challenges in order if you want to exploit fully those nice machines, right? So in the early days of the LHC, it was very easy. Fast progress was following simply some increase of statistics. But as soon as the statistics improve or is accumulated, actually, the statistic uncertainty will become less and less important, and at some point you will really face the systematic wall, right? The systematic uncertainty will become the dominant source of uncertainty that will prevent you from making nice progress or improving your measurement. So therefore, progress requires a better control of all the parametric uncertainties, in particular the knowledge of the PDF or the knowledge of alpha strong, the mass of the top, the mass of the Higgs. So you will need some dedicated measurement to really extract those fundamental parameters, right, of the standard model. Furthermore, you also need to improve your theoretical computation. In particular, you will need to add an extra loop in your computation. And this is well summarized, for instance, in this plot that I've stolen from Gavin Salam, that shows really the uncertainty due to the missing order in the computation. And for various types of processes, Drelian, X production in total, gamma production, etc., etc. And he compares the uncertainty at next to linear order, which is basically available these days, to uncertainty that will be that you will expect at next to leading order. So some of those computations are already available, but some of them are still in the making, right? And the conclusion is that really, if you want to reach somewhere 1% uncertainty, in the theoretical uncertainty, you really need to go to NNLO at least, right? So you shouldn't think that the future of high energy physics is only experimental driven. Theorists also have to work hard, very hard, to actually achieve those computations. So assuming that those computation will be available, you can really extract and make some projection on what all these machines that I've been discussing before will actually achieve in measuring the various Higgs coupling, right? So the coupling of the Higgs to the W, the coupling to the Z, the coupling to the charm quark, the tau, the atom, etc., etc. Right? And each of those bars actually correspond to the various colliders that I've been discussing before. Sometimes also the various stage in energy of those colliders, right? So for instance, here, the light yellow will correspond to the first stage of the linear collider at 250 GeV, and then the dark yellow will correspond to the result when you also add a phase at 350 GeV and a phase at 500 GeV in the next run of these linear colliders. And I wanted to emphasize a few things, right? First of all, if you look at the Higgs coupling to the charm quark, you will notice easily that this is something that the LHC cannot achieve. Right? You will really need an E plus E minus collider in order to measure these couplings. Right? And furthermore, there are also some of the couplings, in particular the one that will be limited by statistics, like the coupling to the photon or the coupling to the muon, the coupling to the Z on the photon. Those couplings will improve dramatically. When you will try to combine actually the knowledge that will be accumulated at end of high luminosity phase of the LHC together with the future measurement at the future collider alone. So this first plot, were corresponding to the sensitivity coming from the measurement at the future collider alone. And this is what you will obtain when you do actually the combination with the measurement that will be achieved at the end of high luminosity phase of the LHC. So clearly for all the channels that are statistically limited, you see a big improvement coming from this complementarity in the two types of colliders. Okay. There is also another type of synergy between electron and proton, right? In particular, when you're trying to measure the invisible, or if you want, untagged or exotic brushing ratio of the Higgs, right? So clearly, Hadron Collider, you can already measure the invisible brushing ratio, because invisible, you can really tag by missing energy. What is much more difficult to measure at an Hadron Collider, simply because you measure only the product of the production times the brushing ratio, is actually the width of the Higgs, so namely the untagged brushing decay ratio of the Higgs boson, right? So here, we reported a sensitivity, for instance, at FCC-HH, which is a sensitivity of the order of 1% in this untagged brushing ratio of the Higgs. But this is only possible because you have FCC-EE before FCC-HH, right? Without FCC-EE, you wouldn't be allowed at all to measure this untagged brushing ratio of the Higgs boson. there is also type of nice synergy between, let's say, FCC-EE and FCC-HH. You know, when you look, for instance, at the top Yukawa coupling, right, you will see that FCC-HH can achieve a sensitivity which is below 1%, right? But actually, when you try to dig out where this sensitivity is coming from, you will see that it's actually determining the top Yukawa coupling via the measurement of the ratio of TTH over TTZ. And if you want really to extract the top Yukawa coupling, then you need to know with high accuracy TTZ coupling. And this is what FCC-EE will achieve before it turn to HH option. Right? So this is one nice, again, nice example of why we need first an E plus E minus and then go to hadron colliders. Right? There is also, you can also see nicely here, you know, for instance, when you're comparing FCC-EE at 250 GeV with FCC-EE at 360 GeV, you see that, for instance, the coupling of the X to the W significantly improve, right? But what is puzzling in this formalism is that still, you know, the uncertainty of the coupling to the W remains quite different than the coupling of the Z, right? In the sense that there is no custodial symmetry imposed on the X coupling at this stage, right? And this is simply because in this formalism, you were looking only at the X coupling independently of what is known elsewhere, in particular, what you have learned previously from electric precision measurement that kind of dictate that there should be a custodial symmetry in physics beyond the standard model, if it exists, right? And this kind of, merging of the various data set, you know, when you're trying to merge electric precision measurement together with X data, together with dye boson measurement, can be well done if you're using an effective field theory approach, right? So of course, in doing this effective field theory approach, you are making assumptions. So for instance, you are really making that that new physics, beyond the standard model, is AV, such that it can be integrating out, and you can really capture all the effect of new physics in terms of contact interaction among the particles of the standard model. Right? So using this this EFT formalism, you can really now try to fit all the data together with X data, but also with electric precision measurement coming from lab or direct electric precision measurement that will be performed at these future colliders. And this is a result that you will obtain. Again, the various bars in this plot represent the various colliders. And you see basically that for almost all of the coupling, you know, almost all of the collider will reach a sensitivity which is below 1% in all the measurement of these couplings, right? And at the bottom panel of this plot, you really see the improvement compared to what will be known at the end of the high luminosity phase of the LHC. And you see that for various couplings, you know, some of the colliders are improving by more than 1 order of magnitude beyond high lumi LHC. So there is certainly life beyond high lumi LHC. Right? So nonetheless, I mean, there is still a way to improve this kind of fit that were done using mostly inclusive measurement, right? And in the sense, they don't do justice to the richness of kinematical distribution, which are accessible either at leptonic machines, thanks to their clean environment, or at high energy hadronic collider that will really probe IPT distribution, right? So in the sense, exactly like what Nima was explaining to us, it's important to look at this tail of this distribution in IPT to really explore the off-shell coupling of the X, right? For various reasons that he explained for the hierarchy problem, but also to learn, for instance, whether the X is really the adjunct of WW scattering unitarization, right? That really relies on the value of the X coupling at high energy and not the value of the X coupling around the weak scale that follows actually from the measurement of the inclusive data. And also it was realized that using the IPT distribution actually help, in a sense, the accuracy, right? Simply because you are really using the fact that BSM effect actually tend to grow with the energy. So you can really go into some poorly populated phase space region where actually the systematic will be in existence. And then you can really use the few events that you will get via this growth of the amplitude with the energy, right? So there have been various examples that really use this fact, for instance, Drellian production, to really put some interesting bound on oblique parameters y and w, right? So the p to the 4th interaction that really captures the universal series. So now I would like to come back again to the question of the interplay between the Higgs and electric measurement, right? So assuming that really the Higgs is part of SU2 doublet, you know, there are some various coupling of the Higgs, like for instance, the Higgs decaying into a ZZ star or 4 lepton, you know. This contact interaction is actually already probed simply by looking at the Z coupling to 2 fermions, right? Simply by replacing one Higgs boson to its vacuum expectation value. In the same way, the Higgs coupling to 2W is actually connected to the triple gauge coupling simply by the Gaussian equivalency, right? So this means that, you know, you shouldn't waste your time looking at Higgs couplings here, simply because the previous measurement of Z coupling or this anomalous gauge coupling already put some strong bonds via this identity, right? So that was really the case at the time of the LHC, right? I mean, electric precision measurement were very strong enough not to interfere with the extraction of the Higgs coupling. So in that sense, there were really 8 Higgs primaries, so namely some deformation of the standard model that were constrained at leading order, at least only in Higgs physics, right? But this is not true any longer at future colliders, simply because the Higgs measurement will improve dramatically, and then the measurement that were performed at LEP won't be enough, you know, and they will actually compete directly with the Higgs measurement. So you will really need to do a full EFT fit of the Higgs and electric data at the same time, right? In a sense, you cannot block diagonalize your fit, right? And this prompted me actually to look actually at what kind of a new electric precision measurement will be needed at the future E plus E minus collider to actually extract with the highest accuracy possible the value of the Higgs coupling, right? So in the sense, I mean, I will compare 3 different scenarios of electric precision measurement. The first one, I will simply use, you know, electric precision measurement that were performed at LEP or SLD, you know, at SLAC. And then I will see what the future E plus E minus colliders can actually achieve, you know, in improving this electric precision measurement. And then ultimately I want to compare, you know, with a perfect situation where I will have an infinite number of these, right? And then I will draw basically the sensitivity in the extraction of the Higgs coupling in those various, in those 3 scenarios, right? And this I will do for the various colliders that we have been discussing. So for FCC-EE, first of all at 250 GeV, and then including also a run at higher energy. And I will repeat the same story for a linear collider or for click, right? And this is the result at the end of the day. This is a very busy plot that gives you all the sensitivity of the various Higgs coupling, you know, at the various collider for these 3 different electric scenarios. So this is a very busy plot, and I will try to read it to help you reading this plot for you. So first of all, I will start taking the ratio, you know, of let's say the real electric precision measurement compared to the perfect scenarios, right? Where I will really assume that you have no uncertainty in the electric precision measurement. And then you will start noticing a few things, right? First of all is that for, let's say for FCC-EE, you know, the fact that you will be able to perform new Z-pole measurement will dramatically improve the sensitivity on the extraction of the Higgs coupling compared to the situation where you will be using only electric precision measurement that have been performed at LEP, right? So the improvement is of the order of 50%, for instance, in the extraction of the coupling of the Higgs to the Z or to the W. And the other thing to notice is that also the electric precision measurement that will be performed at FCC will be close to perfect. About 10% improvement will be only expected if instead of 10 to the 12 Z's, you go to infinite number of Z's, you know, with no systematics at all. So 10 to the 12 is equal to infinity as far as the number of Z's is concerned. On the other hand, I mean, if you try to look at the situation for the linear colliders, you know, the situation is slightly different simply because the linear collider doesn't foresee a new Z-pole run, right? So basically, you will have to live with an electric precision measurement that have been performed at LEP, right? And you will see here that basically compared to the perfect electric precision measurement, you have a degradation of the order of 30%. So the impossibility of redoing a full Z-pole run at a linear collider basically prevent you for improving the Higgs measurement by of the order of 30%. This is not totally true, because even if the ILC doesn't foresee, a dedicated Z-pole run, still you will still be able to accumulate some data at the Z-pole simply by the radiative return, simply by using initial state radiation. You will lower the energy and then you will accumulate some Z in this way, right? Yes. And you can see here the impact of this new electric precision measurement that will be performed using this radiative return. So there is a slight improvement of the order of 10 or 20, 10 or 15%, really using this dedicated Z radiative return data. Right? You should also notice that, 5 minutes, yes, okay. You should also notice that what I was saying actually is mitigated if you are able to run at two different energy states, right? So for instance, if you have a linear collider at 250 GeV plus a linear collider at 500 GeV, then the impediment coming from the left electric precision measurement is actually shrinking significantly, and you are getting close to perfect electric precision measurement. So that was the first impact, really the impact of a new electric precision measurement at E plus E minus collider. Then the second impact is really the use of beam polarization, which is really a characteristic of circular machine, right? So first of all, you should remember that beam polarization usually is a way to increase the rate, right? Simply because you have, again, a chiral series, so the cross-section depends actually on the polarization. And for the polarization that is foreseen for the linear collider, you can actually have an increase in the rate of the order of 40% at 240 GeV. So 40% increase in the rate means that you can improve actually the determination of the couplings of the order of 10% or 6%, right? But if you really see actually the benefit of beam polarization in the extraction of the X coupling, it can actually be much larger than this 6 or 10%. It can reach an improvement of the order of 80%, right? In the extraction, for instance, of the X coupling to the W or the X coupling to the Z, right? And the reason behind it is simply that actually when you are running the machine with two different polarizations, you're actually decorrelating some observable. In a sense, you're really introducing more observables, and these new observables actually are enough to remove some flat direction that are endangering the global electric field that I was discussing before, right? So that's why really you have this huge gain, by using beam polarization, simply because you are decorrelating some observables. Okay, so a few questions that we are left with. I mean, the first one is actually, how did we end up into the electric vacuum? I insisted at the beginning that one big thing that we have learned from LHC is actually the structure of the electric vacuum, but we still don't know actually how we have reached this electric vacuum, right? It could be like in standard model or it could be like in Technicolor when you have a strongly interacting series that also contribute to the breaking of the electric symmetry breaking. And the dynamics of this electric phase transition could have some very interesting consequences, for instance, on the dynamics of the electric phase transition, the production of gravitational wave, or the baryogenesis, for instance. Yeah, maybe a super cool phase transition. But there are also questions that we still don't know, right? Whether the electric vacuum actually corresponds to a global or local minimum, right? You all know that if you try to include some quantum correction to the X potential, you will then generate this runaway minimum at a scale of the order of 10 to the 11 GeV or so. So this means that the electric vacuum will be unstable. It's unstable, but its lifetime is very long, something like 10 to the 161 years, so much larger than the age of the universe, that will make this electric vacuum only metastable in a sense, right? And this could have also some very interesting cosmological implication. For instance, for X inflation, you can really use the X field as an inflaton, but you can also have some interesting signature. For instance, you can produce gravitational wave or form some primordial black hole due to the fluctuation of the X, with some signal that has been computed to be detectable at future gravitational wave detector like LISA or Einstein telescopes. Right? So there are some interesting signatures there. Another interesting question is, of course, related to the hierarchy problem. So we have already had several talks related to the hierarchy problem. I mean, supersymmetry might still be the solution to this hierarchy problem. Nonetheless, there are still other interesting solutions that happen in the market these days. And I think one interesting conclusion that comes out of these new models that are appearing is that often those new models actually introduce new vacua in addition to this electric vacuum. So this means that actually the electric vacuum can be selected dynamically, maybe using this kind of relaxation mechanism, or simply maybe by looking at the inflation expansion of the various vacua, we could end up into the right electric vacuum. And what are the phenomenological consequences of this electric vacua is simply that they open up actually the signature that you could look for, and they could really have some interesting signature, first of all at collider frontier, via this invisible X decays, but also in astroparticle frontier, maybe in superradiance or in dark matter halo, and also in the precision frontier, simply due to the fact that the X expectation value in the sense can oscillate, so it can change the size of the atom, for instance, something that could be detected very easily. So that's why there is certainly interest, in probing BSM physics via precision measurement. I mean, we have learned in the talk by Matthew Rees earlier this afternoon, that there is some nice improvement in the measurement of EDMs, of various particles, starting with the electron, but also some quark or even some big nuclei. And this significant improvement have some nice interpretation in terms of probing physics beyond the standard model. There is also some nice improvement that are foreseen, in lepton flavor violation measurement, like mu to E gamma or mu to 3E, and that will be used to probe various interesting scenarios of physics beyond the standard model. And maybe I would like to conclude simply by mentioning also the nice progress in atomic physics, and we can use actually the superb sensitivity in atomic clock measurement, something like 10 to minus 18 in the relative uncertainty. And you can really use sensitivity to detect maybe new long-range forces, right? And the way to go is, for instance, to measure the isotope shift, for various atomic frequencies, right? And standard model physics, or if you want standard QED, predicts some linearity among these various isotope shifts, and non-linearity, if you want coplanarity, actually will be directly a measure of physics beyond the standard model, right? And you can really see the improvement in this sensitivity in the future isotope shift measurement, and you can reach a sensitivity of the order of 0.1 megahertz for the calcium isotope, for instance, right? And this will allow you to probe some interesting region of parameter space for the coupling of very light new physics, right? And I should mention that very recently, almost as we speak, there have been some very nice measurements that have been performed, for instance, using ytterbium, probing linearity with the isotope of ytterbium will reach a sensitivity of 300 Hertz, and the calcium will reach a sensitivity of 20 Hertz. And you can really see that you will start probing region of parameter space that cannot be probed, for instance, with G-2 of the electron, right? That can be related to some anomalies like the famous barium anomalies, right? Okay, so it's time to conclude. So the Higgs discovery really revealed a non-trivial and rich vacuum structure, but actually the true vacuum of our world might have an even richer structure than the one predicted in the standard model. So there are exciting promises for great discoveries at different scales. And I think all the projects of Higgs factories have a rich potential to outperform high luminosity phase of the LHC, to ensure legacy measurement that will go into all the textbooks, and also to improve the reach in BSM discovery and to provide a refinement in our understanding of nature concerning, for instance, the dynamics of the electric phase transitions, the question of naturalness, etc., etc. And at the same time, these Higgs factories are complementary to a vibrant and diverse program that involves various facilities that I've listed here. Right? So thanks a lot.
Thank you very much, Christophe. Okay, so at the moment, I don't see specific questions. We have one here. Alexander Alves asks, despite less than 10% of the planned total amount of data that has been reached until now, some influential people feel pessimistic about LHC prospects for BSM physics, and that building new high-energy colliders might be a waste of money, that we should focus on other kinds of experiments. What could you say to cheer those people up? Or maybe whether you cheer them up or not. What is your true opinion?
Well, I think there is really an important thing, to know the knowledge of the various Higgs coupling to the sub-percent precision. And this can never be achieved at high luminosity phase of the LHC, even in the most optimistic scenario where you scale up, all the sensitivity with all the improvement on theoretical uncertainty, you will never reach below 5 or 3%, right? And there is a lot of things appearing really if you reach below 1%. So that's one argument for precision measurement. And second point is also to really probe high energy tails, right? I mean, like really exploring the high energy frontiers, exactly like what Nima was saying, right? Really probing the off-shell Higgs coupling is really important to answer many important questions in physics, right? And this you cannot achieve again at high luminosity phase of the LHC.
Got it. Indeed, if I could just sort of ask the same question slightly differently, the business of, for example, living off tails, or the question is whether we've already started to asymptote close to the ultimate physics, BSM physics reach that we could hope to have. And yes, we can go a little further, or you feel like there's a lot more potential. Maybe that's the sense of the question.
I mean, of course, it depends on the scale of new physics at the end of the day, right? But there is certainly many scenarios where you see some limitation, at high luminosity phase of the LHC, and jump. I mean, one order of magnitude in the jump of the energy is really significant, right? So, I mean, physics at 100 keV is really fundamentally different than high luminosity phase of the LHC.
Very good.
I mean, also in terms of probing, the scale of the Higgs potential, right? I mean, you are probing really some interesting scale that won't be accessible at high luminosity phase of the LHC.
Very good. Okay, thank you. Thank you, Christophe. I think we'll pause. Jen actually had a quick question. Could you comment on the physics impact from the recent EFT development, such as generalized positivity, amplitude, soft limits, NLO, effective field theories? Can they play a role in our evaluation of the relative importance of different future programs?
So as far as I know, I mean, all these positivity constraints actually are bounding mostly dimension 8 operators, while here, all this feed that have been done is really looking at the leading effects, so mostly the dimension 6 operator. There are few scenarios indeed that could be interesting, that will show up in dimension 8, like this remedial scenario where you have, the longitudinal component as well as the transverse component of the W and the Z that are composite. And these scenarios are really characterized by a different power counting that really single out some dimension 8 operators that can be affected indeed by those dimension 8 operators. But for most of the scenarios of physics beyond the standard model, they are really constrained by dimension 6, and on those dimension 6, there is no positivity constraint.
Got it.
There is not enough derivative on the operators.